おはよう、皆さん。こんにちは、こんばんは。お元気ですか？本日はバストコンバータのたらくほど、に勉強します。思ったより難しいけど頑張ります。でも、英語で、続きましょう。Of course, I'm not talking about the Japanese for all the video, but today we're talking about the boost converter short circuit, short protection. So basically, why this is an important topic? Because when you design a DCC converter in a boost topology, you don't have any protection from the input to the output. For instance, if you take the back has the high side, and thanks to the high side Q1, you are able to separate the input from the output. Unfortunately, this is not the case of the boost, in which you have the inductor between the input and the switching node be switching. And here you have the MOSFET, and here you have the high side diode. So that's the issue. Q1 has no possible help to provide a protection between the output and the input. So there are several solutions. The first solution, of course, every solution depends on how much money you want to spend. Of course, if you have the ICs like LT404041, these are ICs with shutdown, feedback pin, current control, and etc. But let's suppose that you don't have any means to control the current, and you have only the voltage control. So what you can do in the worst possible case, you don't even have any driver. You want to an industrialization. You want to really to industrialize solution with less money as possible. Okay, so you want to go for this solution instead. Well, the architecture is basically that your boost converter, okay, you basically add a series MOSFET in your load. So when does a short happen, this MOSFET gets open and separates your input from the output. And not only that, but when you have let's say when you have a comparator which somehow turn this guy on, this comparator also has this kind of signal which basically shut down your gate VG, which will be fed in your MOSFET. Just assuming. Now what we want to do is to implement this concept in LTSPICE. Problem is that this MOSFET here is very difficult to turn it on because it's an high side, and being an high side, it means that this op amp has to produce a voltage which is higher than the output. So it's not very easy. It's not easy, okay? Because this MOSFET has basically to stay on always. Okay, so this MOSFET will be an NMOS. Okay, and this MOSFET has always to be on. Okay, so it's not easy. And the voltage of the gate, VG, has to be higher than the VS. That's the issue. To do this, you need a charge pump. Now, I don't want to complicate the simulation more because it's already hard how it is. So let's do this. And moreover, we can't use the ideal source to just turn it on the MOSFET, because in order to shut down, you have to implement the low side driver, because you cannot connect this guy to another source because it will make some LTSPICE errors. Yes, you could use a resistor here, other stuff, but let's make things properly, okay? So let's use the input voltage of 10 volts. Let's have the 3.3 micro and a switching frequency of 150 kHz and a duty cycle of 0.65. The 0.6. The reason why I put 0.6 is because I want you to understand that with the inverting level shifter you will have different result. Okay, so now let's put the NMOS here. I want to use an NMOS with possibly which has a way lower gate drive, gate charge. Sorry. So let's use This guy from the Infineon seems really, really nice. And we want to also to put the diode D. Okay, we put the diode D and 150 micro should suffice. Now we want to put the breakdown to choose a Schottky with a breakdown and a E average E strong enough for our purposes. Remember that we want 24 volts, 10 amp, okay, but we want also around 95% of efficiency. If these conditions are not met, it means that it is not a DC-DC converter. Okay, so this is very, very important. So before going on, we want at least 95, 94, 93, 94, 90, at least some efficiency which has to be okay guaranteed. So now we want to put a current load of 10 amps. If you have an efficiency of like 85% or something, it means in high load, it means that something is not working in your DC converter, and it will probably explode. So now let's generate the triangular waveform, okay, between 0 and 3.3. And the rest time is very short as always. The T-on is d over fs, and the period is always 1 over fs. Now, since we want to implement some sort of enable logic that this has to shut down, let's implement it right away with an ND gate. So I want to use the I wanted to use the logic theorem that states that basically when you have 1 and x is equal to x and 0 and x is equal to 0, meaning that if the signal here is the enable, then when the enable is equal to 1, the signal is equal to x, which is our square wave. When enable is 0, then 0. Very easy. So let's put now the enable. For now, we will put it to exactly to 3.3 volts, so that we don't care. And I will put exactly the negated signal here, just because here I'm going to use a inverting level shifter. Okay. We want to make it fast, so we need to have some acceleration techniques, okay? And we want to provide at least 2-3 amps. So let's select for the totem pole this guy here, and for the MPMP, let's select this guy here, which has a lot of current. And now let's connect them everything to 50 volts. Let's see if this is enough. Okay, if this is enough, then it's good. Okay, let's put 1 ohm always as a protection. Let's go a bit away. Ooh. Okay, let's go a bit away. Now, for the sake of the grounding, please remember always to connect the low side, the low side properly. Okay, not connect to any ground. You want to make a beautiful ground connection. This is how it should be connected. Okay. And let's use also the logic. So between this point and this point, we wanna have 50 volts. Now, if this is enough, then okay, I'm very happy. So let's see what's going on. This is the enable, and this is the signal coming out. Oh, no. One is not good. Sorry. So we need to adjust it right away. So VLogic, V high is equal to 3.3 and V low is equal to 0. Okay, this is very important and make it visible. Okay, so that's the first mistake that I found. Now, the gate resistor. Okay, don't want to make the transistor explode. Okay, so now we have between 0 and 0.7. And how much rise time we are actually losing? Let's see. No. Oh, this is a disaster. This is a disaster. A disaster. Okay, we need to. Okay. Don't worry, guys. Okay, let's speed it up. We need more speed. Definitely, we need more speed. We are losing too much rise time and too much duty cycle. No. We need acceleration. We need acceleration immediately. Okay, so how we can accelerate? First, let's put the acceleration capacitance between the out between in the base. 50 pico should be enough, and we always we can also make faster to the turn off, I guess. We can also make something there, even though the turn on is more more worrying, honestly. Okay, so let's do this. Let's put an acceleration transistor here. Need more space, sorry guys. Let's put an acceleration transistor here, and let's connect the base. So let's provide an alternative path with this current follower, supplied like this. And from the turn off, we use a Schottky diode. I don't care, this one, honestly, don't care. So now let's run a simulation again. So let's see, this is the input and this is the output. Ah, okay, that is 60 seconds. Oh, well, 60 seconds. Okay, 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 okay. It has like a rise time of, let's skip this delay, which I don't like, but it has a rise time of 20-30 seconds. Okay, okay, I'm pretty satisfied. Okay, okay. The current provided is 1.8 amp. Okay, that is also good. Yeah. Oh, it's nice. Yeah. Okay. Yeah, it's not. Now it's nice. Okay. Yeah, guys, if your level shifter is if your driving circuit is fast, is not fast, you're gonna have a lot of losses. So be careful. So let's finish the transient, and it should be around 24, 25 or something. Okay, so it is. Yeah, 23. Reasonable. Now we want to check effectively that we have this kind of efficiency. Okay, so let's check the load, and we have how much? 2030. Okay, almost like I thought it would be. So let's go to the calculator. 230 divided by the input. So let's see. 247. 247 equal to 93%. Okay, 93%. Okay. So this could be a real DC converter that actually exists and actually can work. Okay. Yeah, you could probably select a better MOSFET anyway, or even a better, 14 watts. Come on, guys. I think that there is, of course, there is better than this. Okay, I'm pretty sure that if you search carefully, I'm pretty sure that you can find better than this guy. Yeah, like 8. Now I have 8 watts. Okay, so I already improved the circuit. So we have how much now? We have 236, but we have less power here. Okay, so the efficiency has definitely improved. And the MOSFET, does it blow up? No, the MOSFET is fantastic. Just 0.5 watts. Ooh, okay. Do we need some snubber? No, we don't, but also because we didn't select any parasites, so it's pretty reasonable. Okay, so now the circuit looks pretty good. Now we want to use the output voltage, we want to just put some kind of now we want to separate the load. So let's make a short circuit simulation. To make a short circuit simulation, we want to use the same pulse here, but with 0.15. Yeah, guys, I don't care of, it's just a short simulation, but we want to make like after 4 milliseconds, okay? So we have the time to end the transient, we have the time to study everything, and then, oh, the node has already changed. So let's run the simulation, and now you should see the output voltage goes down to 0. Well, which it is. So how we can protect the circuit from the short? In a voltage control situation, the only possible solution could be that when the output voltage is less than the 40-50% of the expected output, So, for instance, in this case, it's around 12. It's around 12 volts. Then you can activate. You can shut down the gate voltage that we called here G. Okay, the VG, and then you can activate the MOSFET here that I will select. And be extremely careful of this MOSFET. The reason is that you need to make be extremely careful for this MOSFET because the N MOSFET, okay, so this is the NMOS, it has the body diode going from the source to the drain. And so, for this reason, if when the moment you put this MOSFET in series, you don't have to make a connection between the output voltage like this. This connection is forbidden because then the current just goes through the body diode and you are not interrupting the load. Okay, I will just make an example later by inverting the MOSFET to see what happens. So this is extremely important. So this MOSFET here that we are putting, this MOSFET here that we are putting in series like this, okay, and this is extremely important to put it like this, okay, it has always to be on, always on, but when the output voltage goes down like this, then he has to turn off, and then the MOSFET will be opened from the short circuit. Okay, I despise LTSPICE that it does not put the body MOSFET here, honestly. So the first thing that we're gonna do is to read the output voltage, and the output voltage has always to be read before the MOSFET. So the reading, for instance, 10K, and for instance here 20K. Okay, and now we want to create some logic that basically with the comparator that when the MOSFET goes down, okay, you have to open this MOSFET. Now the problem is to open this MOSFET. To open and close this MOSFET, the gate voltage has to be higher than the output voltage. And yeah, you know how to do that. You know how to do that. Yes, the charge pump. Oh yeah, this is a tremendous amount of circuit. Okay, here you have to provide a square wave, and this is C, D1, D2, and C load. Okay, we can try to implement it later, and this is the V offset. Okay, so basically you have to connect this to the you have to provide a square wave, you have to connect the V offset to the you have to connect the V offset to the output voltage, and this has to be connected to your op amp. Yeah, exactly. So this basically starts from 24 volts and it goes up plus 50 volts. So 24 plus 50 volts, like 39. Yeah, 39. Yeah, yeah. That's the only possible way. That's the only possible way to one of the most possible way to turn on, of course, the this high side. It's very problematic. I know, guys. It's very problematic. Not only that, but he also has to turn on fast because it has a protection from the short. So, oof, you will need something like this, if not even worse, probably worse. So let's make see things step by step, and let's see if you can do everything. Okay. So the first thing that we're gonna see is please allow myself to put a reference voltage of 14 volts. Please don't let me waste time on calculating the comparator or something. Okay. So the T-on is 1 and period is 2. I don't care. And let's put a delay of 3.8 milliseconds. Okay. And what I'm doing now, it's like a monstrosity of electronics which does not exist. But I'm really doing, guys, I'm putting the voltage of 15 volts exactly between this op amp. And the guys, I repeat, I will probably do it later if I have time. But this is the concept. This is an high side, okay? So you don't have any means to turn it on if not by high side techniques. So let me bypass this guy. Let me use also this stage, okay? Because we need to turn it on. And of course, let's separate the bases with at least with 1 kilo ohm resistor, and let's call this one comp, okay? And also this 50 volts has to be used as well in this point here, okay? And now you even want to put the classical diode, which will be again a Schottky, plus your boost up capacitor. 100 pico, sorry, 100 nano. And this has to be connected here. And this one has to be connected to the load. Yeah. Okay. Now, when the comparator goes down, because when the comparator goes to 0, it means that it's gonna open this MOSFET here. So when the comparator goes to 0, then the enable has to be shut down. Okay? The problem is that you want this to happen only after the transient. In LTSPICE, to make a joint condition, like for instance, you want to see a function of f of x, which is x1 and x2, in LTSPICE, this condition can only be written as a product. So you have to say that when the time is higher, is greater than 5 milliseconds or something, and vcomp is equal to 0, then do something. This in LTSPICE becomes time greater than 5 milliseconds times v of comp less than 2 or whatever that will be to avoid oscillation. So let's write it. If time is higher than 4 milliseconds and times v of comp less than 10, for instance, then if this condition is true, then you want everything to 0. Otherwise, you keep the 3.3 volt. Okay. So if this condition is not guaranteed, then you keep switching. Otherwise, you shut down. The little guy here. I just hope that this divider is enough to trigger this condition. So if it doesn't work, don't worry at the beginning. Of course, it will need some fine tuning at first. So here we have 24 volts. Let's make a brief calculation. 24 volts. Then we have a comparator. Okay, a comparator which is 2 over 3. 2 over 3 times 24. We have 16. Okay. Yeah. Sure. That should be it. So this is basically is giving 60 volts. At the moment it goes down, this will be triggered. Okay, I like it. Okay, since this is on the minus, and when the plus is higher than the minus, it is up. And yes, since 14 is no, it's not. It's the contrary. Because this has to be higher, because now this is 16, when this guy is higher than this one. Okay, now it should work. Stop. First. Okay, this guy is oscillating, and the condition starts at this point here. So, I need more waveform to debug. Let's see comp. Okay, okay. As intended, the comparator is always up. Okay, is always up, and then it goes down exactly as I want. And you see, guys, you see, the MOSFET is on. Yes, it is correct. Yes, you see, the MOSFET is on, and then it goes down. And when the VGS goes down, this MOSFET is open. And since it is open, you literally have no load flowing. Yeah, it takes a while, but then it takes a while. Like some microseconds, but then you have zero load. Okay, so it is correct. And the gate shuts up. Yes, guys, we did it at first try. Okay, so as you can see, the gate really shuts down all with this logic that I implemented. I just waited the transient to be over, as you can see 3.8 is enough. So, and when the transient is over, and there is a short circuit, let's make this beautiful short to see here. So the voltage goes down, the output voltage goes down, as you can see. So let's use the Vout. The output voltage goes down, but the gate shuts down, okay? And so the MOSFET is protected. Yeah, the MOSFET, as you can see, is protected, okay? But eventually, also the input will be protected. Yeah, just give him some more time, and then it will go to 0. Yeah, guys, we made it. We made it, guys. Yeah, this is how actually it should work. Now, forget the timing because this is just a concept simulation. If we want, we could really implement the charge bump. Okay, because now what you see is that implement this 50 volts here. Okay, and naturally this cannot exist. Okay, you have to implement a charge bump. To implement the charge bump, you need first a square waveform, which can be something like this. Okay, let's use the square waveform, and this can be even generated by the microcontroller itself. Between yeah, let's keep the level shifting. Let's keep the level shifting and stuff. This should be fine. Now, I did wrote the charge bump here. So let's use some values which make sense, like the micro. The thing is, will the charge pump charge fast enough? Oh, sorry. Oh, come on. Okay. Will the charge pump charge fast enough for the circuit to activate? Worst possible case, I will have to translate everything later. So this is the most idiotic charge pump that you can really find on the market, okay? And that you can really that you can also really do it yourself, but it should work. So let's also run the simulation again. Now I am more focused on the charge pump. So let's see. Yeah, guys, it works. Okay. So as you can see, I have I do really have my 14 volts, so I can delete this guy. I can delete this guy. Okay, I can just delete this guy. I just have after 1 millisecond, so there should be any problem. And yeah, I can just use poop, just do something like this. And now we even come on. We even implemented the charge pump. Where do I have some space? That's the neat part. I don't. I just want to have a little bit less ripple, so I will just use 25 microfarad, okay? Just to have a little bit less ripple, okay? Now this is connected, this has to be connected to the output, so we just put out here. Ah, okay, now it becomes a problem of connection. But there shouldn't be any problem because VOP plus in this way I'm just shorting the output with the load, which is not what I actually want. So let's see. Yeah, this should actually work anyway. This should actually work. Let's run the simulation, but this should actually work as before. No, I'm not. No, no, no. Now there are some problems. Yeah, of course there are. It's never easy. Of course there are some problems. It's never easy to activate a charge pump really in simulation. Because I cannot connect the -2 here, otherwise I will. Okay, forget it. Okay, it's not important anyway. Let's just leave the charge pump like this as a concept, okay? But of course, with more time and patience, this has to work, okay? This has to work because eventually you have to provide really 50 volts between plus and minus, okay? So in the end, now let's forget that surely there are some problems regarding some stuff that I don't want to investigate because it is hard and you may think, but this, conceptually speaking, it has been a very good ride. I'm very proud of this simulation, okay? and and our short circuit has been really, really beautifully protected. Maybe before it was right, but it's just changed the node. Yeah, probably it was. Probably it was right anyway. It's just changed the nodes, but I don't care. Anyway, thank you for following, guys, and see you in the next video. Bye bye.